Hello guys, and welcome to an Arduino tutorial on how to make a light Theremin using a buzzer and a photoresistor. This tutorial is part of the Ultimate Arduino Beginner's Guide series, and this is the 8th lesson. Let's get straight into the Arduino code then. What is a light Theremin? Well, a theremin is an instrument that makes sounds based on the movements of a musician's hands around the instrument. The theremin detects where a performer's hands are in relation to two antennas by reading the capacitive charge on the antennas. These antennas are connected to analog circuitry that create the sound. One antenna controls the frequency of the sound, and the other controls volume. The Arduino can't do the sound. I'm not going to in this project, but it will detect the amount of light using a photoresistor and then make a different sound on the buzzer. Okay, so for this lesson you will need an Arduino clone, a solderless breadboard, jumper wires, a photoresistor and a piezo buzzer. We haven't used a photoresistor or a piezo buzzer yet, so this is quite an exciting project, but quite a lot of complicated code too. This is a wiring diagram for this project. I suggest you pause it for a couple of seconds to get this wiring done, but please note this black wire here should be this resistor, but I'm using a software company program called Fritzing, and Fritzing I couldn't find this particular resistor that you need to use, so get that done and I'll see you in a couple of seconds. Okay, you should have that wiring diagram done now. I'm going to explain to you a bit about pulse width modulation. Now, we did some of this last time, so if you want to skip this bit, that's fine. But if you can't remember it, then you need to listen. Pulse width modulation, or PMW, is a technique for getting analog results with digital means. Digital control is used to create a square wave, a signal switched between on and off. This on-off pattern can simulate voltages in between full on 5 volts and off 0 volts by changing the portion of the time that the signal spends on versus the time that the signal spends off. The duration of on time is called the pulse width. To get that varying analog values, you change or modulate that pulse width. If you repeat this on-off pattern fast enough with an LED, for example, the result is if the signal is a steady voltage between 0 volt and 5 volt, controlling the brightness of the LED. So in this graphic, the green lines represent a rectangular time period. The duration or period is the inverse of the pulse width modulation frequency. In other words, with Arduino's pulse width modulation frequency at about 500 Hz, the green lines would measure about 2 milliseconds each. A call to analog write is on a scale of 0 to 255, such that analog write 255 requests a 100% duty cycle always on, and analog write 127 is a 50% duty cycle on half time, for example. And we've got some little diagram here to show that. Now here we've got another diagram. Now in this project, what we're doing, these are the different tones that are going to be made using pulse width modulation. Now, while the Arduino can't exactly replicate the sounds from the light from a theremin, it's possible to emulate them using the tone function. Okay, this little diagram here shows the difference between the pulses emitted by the analog write and tone. This enables a transducer, like a speaker or piezo, to move back and forth at different speeds. So, normally, we'll be using analog write with pulse width modulation. Now, we are using something slightly different called tone, and it enables a transducer, like a speaker or piezo, to move back and forth at different speeds. So, look at this one here. Notice how the signal is low most of the time, but the frequency is the same as pulse width modulation 200. Okay? Then look at this one here. Notice how the voltage is high most of the time, but the frequency is the same as pulse width modulation 50. And then look at this one here. the duty cycle is 50% on half the time, off half the time, but the frequency changes. And then look at this one here. Same duty cycle as tone 440, but twice the frequency. And this is a 10 millisecond time period. Okay, so hopefully you should understand a bit about that now. So we're going to go on to the main part of this tutorial, which is the code. Now, the code that we're using today is quite complicated. And we haven't done much of code like this in previous lessons. So a lot of this is brand new stuff. Right. So these three little things here are variables for calibrating the sensor. You need to create a variable to hold the analog read value from the photoresistor. You need to create variables for the high and low values. You're going to set the initial value in the sensor low variable to 1023 and set the value of the sensor high variable to 0. When you first run the program, you'll compare these numbers to the sensor's readings to find the real maximum and minimum values. Hopefully that makes sense to you. And then you need to create a constant named LED pin, which is 13. Now, for this project, we are using the onboard LED connected to pin 13. So you don't need to use an external LED. And it's an indicator that your sensor has finished calibrating. Something useful that you can use. Now we're going into the void setup function. Now, we've put here pin mode LED pin output. We need to set it to output so we can turn the light on. And then we've said here digital write LED pin on. So that's pretty simple, we're turning the LED on. So after it's calibrated, the LED turns on to signify that. Okay, now we're getting a bit more complicated. Code that we've never done before. So, we need to calibrate the sensor's maximum and minimum values. So we need to use a while statement to run a loop for 5 seconds. While loops run until a certain condition is met. So in this case, you're going to use millis function to check the current time. Millis reports how long the Arduino has been running since it was last powered on or reset. Okay, and then let's have a look at this bit here, sensor value. So in the loop, you'll read the value of the sensor. If the value is less than sensor low, which is initially 1023, you'll update that variable. And if it's greater than sensor high, initially 0, that gets updated. So this little long piece here, this basically just updates the two variables of sensor low and sensor high. Okay, now let's go on to this little piece here. This little piece of code, digital write LED pin low. So when 5 seconds have passed, the while loop will end, and we turn off the LED attached to pin 13, and we'll use the sensor high and sensor low values just recorded to scale the frequency in the main part of your program. Okay. Now we've got a little bit more code to go through, yeah? Now, we've got a loop here. Now in the loop, read the value on A0 and store it in the sensor value. So, this is what we're doing here, okay? We're reading the value on A0 and storing it in a variable sensor value. Now that will either be like high or low. And then we need to create a variable called pitch. The value of pitch is going to be mapped from sensor value. It's going to be mapped from sensor value. Use sensor low and sensor high as the bounds for the incoming values. For starting values for output, try 50 to 4000. These numbers will set the range of frequencies the Arduino will generate. So this 50 and 4000 here is the frequencies that the Arduino will generate. And then here, next we need to call the tone function to play a sound. It takes 3 arguments: what pin to play the sound on, in this case it's pin 8, and what frequency to play, which is determined by the pitch variable, and how long to play the note. Now, you need to start off with 20 milliseconds to start. You might want to increase it or decrease it depending on how it goes. And then we need to call a delay for 10 milliseconds to give the sound some time to play. If we didn't have that, it'd be all messy. And that's all the code that we're using, and I want you to challenge yourself at this part. Right, traditional theremins can control the frequency and the volume of the sound. In this example, you'll be able to control the frequency only. While you can't control the volume through your Arduino, it's possible to change the voltage level that gets to the speaker manually. What happens if you put a potentiometer in series with pin 8 and the piezo? Or what about another photoresistor? So try that out as today's challenge. And if you struggle with that challenge, it doesn't really matter, but see what you can do. Really? Okay, so there's been a lot of new stuff today, and you might not have understood it all, but I hope that you've understood quite a lot of it. If you haven't, or you're stuck on anything, please feel free to email my email, which is unofficialarduinotutorials@gmail.com. And that's it for today. Thanks for watching, and be sure to watch my many other Arduino tutorials. We're about halfway through the course now, and we're starting to get more difficult, but don't worry, that lesson was a lot more difficult than the others, but next lesson we're going to be going back a little bit and looking at more of the basics, I think. So thanks for watching, and be sure to watch my many other Arduino tutorials, and I'll see you next time. Goodbye.